Hi there, this is exercise 10D for Year 12 math students. Some of you again will have seen this in class with Miss Frovine's lessons. The other class, Miss Stanley's class, with me did some of this. We introduced it but didn't do any of the exercises. So in case some of you weren't in, I'm going to do this lesson now. Some of you will be able to jump straight to the exercises, I suspect, but just be careful. There are some tricky bits, so you might want to just go through and run through these problems again initially as I introduce them, and then go on to the exercise. So this is our first identity. It's a trigonometric identity, and as you see, it says tan theta equals sine theta divided by cos theta. Now there is a proof for this, and if we think about the right angle triangle ABC, obviously you can see on this you've got the B, which is opposite the big B, and that's the standard way of doing it. The A is opposite the A, and the C is opposite the C. So it doesn't really matter which way you go about defining what they're called. I'll just turn my pen on. I'm not sure it was. Oh, that's better. As long as the standard way, as I say, is the little c is opposite the big C, and so on. So anyway, what we're going to do is just run through a proof of this identity. And then you can see it in action. Now the first thing to note is just from SOHCAHTOA. So you'll notice here, I'm trying to find where there's my pen. So if I was to write SOHCAHTOA here, very neatly obviously. So SOHCAHTOA says how these sides are related in the right angle triangle. So over here we've got, this is obviously the opposite, this is the adjacent, and this is the hypotenuse. So given those three things, you can now see over here why it says cos theta is A over C, because cos is the adjacent over the hypotenuse, A over C, and sine theta is B over C, opposite over hypotenuse. And both of these equations then allow us to be rearranged, and if I move the C over there, I get that A is equal to the C cos theta, and again I move the C over there, I get B is equal to C times sine theta. It's all well and good, but I suppose we could have also written over here what tan theta was, and so tan theta is opposite over adjacent, opposite is B over A, B over A. But of course up here now I've got an expression for A, I've got an expression for B, so it doesn't surprise us really that we can now replace the B with the C sine theta. We replace the A with the C cos theta from up here, and these C's can cancel out, and when I cancel them out I'm left with just sine over cos, so sine theta divided by cos theta. And this is an identity we use loads. Now, do you need this proof? Possibly. Probably not, but possibly. There are a lot more proofs in the new A-levels than there ever was in the old. So this is potentially a proof that you could do and be expected to do in the exam. Doesn't mean you will, but we show you how they work for a reason. But broadly, the one thing I must make sure you know is that this formula is going to be used loads. I should get a little word about this. Really, there should be 3 lines on these. An identity works for all values, not just certain values, and we show that it works for all values by having this identity symbol, which basically means tan theta is equal to sine theta over cos theta for any value you put in. So yeah, you can chuck in any number and it will work. We've got a second identity. This is trig identity number 2, and this is basically we call it Pythagorean because it just looks like Pythagoras' theorem. Pythagoras says a squared plus b squared equals c squared. You can see the similarities there. Well, kind of cos squared plus sine squared equals 1, I suppose. Notice again it's identity. This identity works for all values of theta, any angle. Obviously, very often this is called the x or something, but this here we've got the Greek letter theta representing the angle. I'm sure you've seen theta before. If not, get used to it because you're going to see it a lot more. Just a word of warning, this cos squared thing that they are talking about, well, this is a lazy man's, a mathematician's, if you prefer, way of writing that. So rather than put in brackets and then squared, we just say cos squared, and you have to get used to it. Likewise, sine squared should really say sine theta in brackets squared, but no one ever does. Anyway, let's go back to the proof of this. it's back to this right angle triangle. We've got a squared plus b squared equals c squared. That's Pythagoras bit. A squared, b squared, c squared. But of course, on the last slide, we wrote down what these things were. So some of that will come into play in a bit. There's a trick that comes first, though, and the trick is the fact that on the right-hand side of this equation at the top, it says 1, but mine doesn't say 1. So if I divide c squared by c squared here, I will get the 1. But if I do it to the right-hand side, I've got to do it over here as well. So you'll notice this c squared over c squared has become 1, because if you divide anything by itself, you get 1. B over c, both of them were squared, so I can just write b over c squared, a over c squared. That's fine. And this is where I use what I learnt in my last one. If you remember, if you just go back to this, for instance, here it says that a is c cos theta. Yes, a is c cos theta. Or said it a different way, perhaps better to look at this. A over c is cos theta. So if a over c is cos theta, a over c. And that's why I've written a over c here, and that's why it says cos theta squared. Oh yeah, but don't forget b over c is sine theta, and therefore that's our identity. Cos squared theta plus sine squared theta equals 1. Very useful. So I've got a couple of examples here, then I'm going to show you how we can use it. We've got here that sine x is a third. Well, I suppose that allows me just to do something here. Now we're going to use identities as well. Sine x is a third. So I can go sine squared x. Now remember, that's the square of this thing here. That's 1/3 squared. And if you square a number, you square the top, you square the bottom, that's a 9th. And don't forget that cos squared x plus sine squared x, this is basically the identity we're using, is equal to 1 for all values. So this value up here is fine. So if I want cos x, I can now write cos squared x plus sine squared x, remember that's a 9th, equals 1. Move this over, I get cos squared x by 1 whole 1 minus a 9th, do it on your calculator in your head, is 8/9, and therefore cos x is the square root of 8/9. And again, you can do that on your calculator, and I reckon it's 2 root 2 over 3. There's a variety of ways of writing that, but basically a cube root in the square root in the bottom and the square root in the top. Tan x, similar trick. We could use our trig identity. We know that tan x is sine x over cos x. These are the identities I want us to get used to using. So sine x is, we've worked it out. No, we got told sine x is a third. So that's a third. And I'm dividing that by, where is it? Oh, it's here. 2 root 2 over 3. Now you may recall, you could obviously chuck this in your calculator, but you may recall if you divide by a fraction, you turn it upside down and multiply. And the 3's cancel, and I get 1 over 2 root 2. Now, that you could leave it like that. There'd be nothing wrong with leaving it like that. But if I just do this on my calculator, just to highlight the fact that most of your calculators have probably come up with something else if you've done this yourself, and I get here root 2 over 4. So hopefully that's the answers I've got here. Yes, it is root 2 over 4 and 2 root 2 over 3 for the first answer. And there are a variety of ways of writing these things. Theoretically that's one way, but it's not very simplified. Here's another, here's another. This is what the calculator gives. The new calculators give you nice simplified answers. So the second example, let's see how we're going to do this. Oh, I was just going to say, by the way, this gives me answers in this quadrant. Now, you'll remember we talked about the cast diagram the other day. The cast diagram wasn't needed here because it says that the answers are between 0 and 90. Now, if I get answers which are not in that interval, I need to be a bit more careful. Anyway, given that tan x is minus 2, it says, now this is why I wanted to highlight that out, because look, here is an example where the numbers can be different. It says x is not between 0 and 90, in fact it's between 90 and 180. Now, if I just remind you of the cast diagram, you remember this is 90 degrees. This is, sorry, that's not 0 degrees, 90 degrees, 180. and 270, and I think I remember saying to you, go anti-clockwise direction from this starting point here, and eventually you get around to 360 again. And therefore ours are in between 90 and 180, so our values are going to be in this quadrant. You remember I called it CAST. And I'll come back to that in a bit. That's just a reminder of the cast diagram. Anyway, it says that tan x is minus 2. It says use trig identity to find the exact value of cos x. Well, how am I going to do this? Well, tan x is minus 2. Now I want to just quickly show you a slight different approach, and you might like this, you might not. Well, my pen's gone, bear with me. There's the answer. My pen's still not working. Oh, now my pen's working. So what I'm after here then, I'm going to show you a little trick, quite a neat trick. Very quickly do this. So this is an angle. I'm going to draw that x there. It says tan x is minus 2, and I suppose I could think of that as minus 2 divided by 1, because of course minus 2 divided by 1 is still minus 2. I've not changed that. Why is that useful? Because SOHCAHTOA tells me that the tangent is equal to the opposite over the adjacent. So this is the opposite, and this is the adjacent. So this is my 2, and this is my 1. I won't worry about the minus for now. But what it shows you is that I can do a bit of Pythagoras here, you see. So if I want this distance here, then that what I'm going to call h for the hypotenuse, then h squared is 2 squared plus 1 squared, which is 5. And therefore h is root 5. And that helps because I can now quite easily just go tan x. Now tan x, of course, is the opposite. Oh, actually I didn't want tan x, I wanted cos x, sorry. So cos x is equal to the adjacent over the hypotenuse. Now the adjacent is 1, there it is, based on my description of my triangle down here. And my hypotenuse I've found is root 5. So that's cos x. Well, not quite, because I now need to look at my cast diagram. My cast diagram says cos, all of them, sine and t. This is what shows you where they're positive. Now I am looking in the second quadrant, which is from 90 to 180. So any angle here, the only thing that's positive is sine. So the fact that I've got cos is equal to a positive answer, it can't be positive. So I have to say it's negative because it's in this second quadrant. If it had been sine, it would end up being positive. That wouldn't have been a problem. But because it says cos, it's negative 1 over root 5. Now if you type negative root 5 into your calculator, it comes up minus root 5 over 5, which is the same thing, of course, as the answer down here. So that's all worked out fine. And that broadly is it. I've got some questions for you from exercise 10D. On Moodle, I will put on the exercises for this. I've suggested start on question 1A part 2. I can't remember what was wrong with question 1A part 1. But if you have a look, obviously the early questions cherry pick a bit. You might want to do them all. You might think you need all the exercises and practice to get good at them. You might think, no, they're all the same, I can do these, and just move on to the harder ones. So that's for you to decide how you want to play it. There will be the answers applied as well, and any homeworks will appear on Moodle in due course. I'd appreciate it if you can show me that you have done this by emailing me back when you get this. And that just lets me know that you're up and running and you can do the work and it's all working fine. I certainly wouldn't want you to fail your exams in a year's time because you missed out on this important section of work that we're going to go through over the next few weeks. Any questions, email me, Miss Stanley or Miss Frovine. We're all here to help you. So until then, all the best.